Yeah, so I co-lead the AI for Cyber Defense Research Centre at the Turing Institute, where we do academic research at the intersection between autonomous agents, more broadly machine learning, and cyber defense, computer security. And in this talk, along with Anna, who's going to introduce herself in a moment, we're going to take you on a journey from the lab, where we do this academic research, both within AICD and more broadly, to the sort of operational playing field, where we have to deal with challenges in policy, legal, technical. Along the way, we're going to look at those challenges in more detail, not only the policy challenges, but briefly some of the fundamental research challenges that we face. And yeah, so over to you, Anna.
Hi, everyone. I'm Anna Knack. I'm a senior research associate in the Alan Turing Institute's Defense and Security Challenge, and I'm also the lead researcher at CETaS, our Center for Emerging Technology and Security. I'm not a technical expert, so if you have any difficult questions about cybersecurity, I'm going to throw them over at Chris. But if you have any questions around the so what for defense and security around autonomous cyber defense, or what technical and policy challenges we might encounter if we wanted to introduce autonomous cyber defense in an operational environment, then I'm the person who's probably best placed to answer some of those questions. So why are we doing this work? The problem statement for autonomous cyber defense and all our research, both the fundamental side and the policy side in the Defense and Security Challenge is, what happens when the speed, scale, and stealth of cyber attacks exceed human capacity to respond to them? So we're already seeing a lot of reports around automated cyber attacks, overwhelming the capacity that we have. In a lot of small businesses, they don't even have an IT department, let alone something that could cope with the evolving threat environment as we see it in the future. We're also concerned about stealth. So ahead of the physical invasion of Ukraine, we saw cyber attacks across Ukraine. And there was a sense that we identified the attack and we addressed it pretty quickly. But we also know that after the physical invasion, around a month into the physical invasion, we were still seeing computers across Ukraine shut down and wiped. So there are questions around, are our attacks evolving in sophistication in ways that we may not be aware of? Do we need autonomous agents to be able to help us understand how those attacks are evolving in the future, in addition to helping us cope with the speed and scale of cyber attacks?
Okay, so over the next few slides, I'm going to try and kind of communicate just a snapshot of where the academic research is at in the lab. And kind of what you see on this slide is that there's been this exponential rise in publications talking about autonomous cyber operations and autonomous cyber defense. But to understand why that's the case and what's kind of shaping that work, we need to briefly take a step back and look at the fundamental machine learning kind of AI technologies that are shaping the research. So if I could only tell you about one technology that is kind of having the biggest impact in autonomous cyber defense, at least in terms of the current research, it would be reinforcement learning, deep reinforcement learning more specifically. And reinforcement learning is behind and has enabled some of the most famous and high-profile machine learning systems in the world today. So AlphaZero kind of famously beat the grand champion Go player in 2016. And ChatGPT, right, which needs no introduction. And whilst I'd really love to go into loads of technical detail about deep reinforcement learning, I don't think this is the right time. But I do want you all to leave with a sense of why it's so important and why it might be having such a big impact. So very briefly, in a nutshell, reinforcement learning is a computational approach to learning from interaction with an environment. So you have an agent, and it takes actions in an environment, and it receives back an observation and a numerical reward at every time step. And then what you do is you play the environment, so you repeat this interaction millions or even billions of times, and the agent will learn a strategy to maximize its reward in the long term. And what really separates this from perhaps the supervised learning techniques that you're probably more familiar with is that we don't need lots of labeled data. We don't even really talk about data sets. It's sufficient simply that we can represent our goals or our objectives in a given environment as a numerical reward. And this kind of really makes it very powerful. So if you want to train an agent to be a world-class chess player, right? I don't even need to interact necessarily with real chess players until I kind of evaluate it in the real world. I just need to reward the agent for winning games of chess. And we can take that same capability and use it in a range of environments that are relevant for cyber defense to find high performance and often surprising and novel strategies for achieving relatively arbitrary goals. So with that in mind, finally, I can tell you a bit about what's been going on in the lab. I think very broadly, what we've seen is an explosion in environments for training autonomous agents, both offensive and defensive. I probably, of all of these, have to mention the CAGE challenge, which is the Cyber Autonomy Gym for Experimentation. This was a sort of Five Eyes public project. It's on GitHub. You can go and download this and train your own agent. And I'm proud to say that our team won 2 of the 3 challenges that have taken place to date. But it's very representative of the state of research at the moment, which is that the network sizes are quite small, perhaps 10 or 20 hosts. The environments are simulated rather than being virtualized or real systems. And they operate very abstractly with things like the MITRE ATT&CK framework or the C2 command and control framework. So in other words, agents do things like remove an infection or scan a host as opposed to something that can be immediately translated into real instructions on a real system. Lastly, what we also see a lot of in the lab at the moment, and you see towards the top right of this slide, is these grid world environments. And these are very popular for solving hard fundamental problems in reinforcement learning. Or in our case, things like, can we build agents that adapt to arbitrary network topologies, arbitrary action spaces and observations? Or can we mitigate backdoors in deep reinforcement learning agents? And these very abstract grid world environments allow us to do that without the confounders that you find in a more sophisticated cyber environment. Nevertheless, I'll leave that kind of snapshot of the lab with the thought that just solving those problems doesn't, in and of itself, demonstrate that we can solve them in real cyber environments. So we still have a way to go there. Mm-hmm.
So lots of exciting potential. So to understand how we could potentially scale up some of the promising research that Chris is leading in the AI for Cyber Defense Center, the Alan Turing Institute assembled a multidisciplinary team along 2 tracks. One led by Chris through the AI for Cyber Defense Research Center, which he can say a little bit more about in a moment, and a series of projects that I'm leading for the National Cybersecurity Center through our Center for Emerging Technology and Security on autonomous cyber defense. The first study sought to understand what the possible bottlenecks Chris's team will probably encounter when they try to scale up this research and what they need in order to scale that up. And also looking at the policy challenges, like for example, like what does it mean for skills and workforce requirements? What does it mean for new policies that we might need to adapt to the speed that these operations are going to be deployed at? And what do we need to understand about promising practice or lessons learned from other projects that have sought to scale up AI capabilities for defense and security, and how might that apply for this specific use case? Do you want to say a little bit about CD?
Yeah. I also want to add, I think one of the biggest reality checks that we got from your work was the appetite in the operational landscape for autonomous systems. I think in the lab, right, we're just super excited. Let's just build these agents, cause chaos. That's great. It's lots of fun. But in reality, there's that's unwilling to be. There's certainly resistance to that, which is something that we have to contend with, and that brings in a bunch of technical challenges on its own. I mentioned AICD works at this kind of intersection between autonomous agents and cyber defense. We kind of go about that as a pretty mixed team. So we've got some real machine learning specialists, statisticians, and the like, and some security experts. And we pick, ideally, real-world cybersecurity problems, privacy problems, apply the very latest, techniques for autonomous agents, deep reinforcement learning, large language models more recently, and then generally find that a bunch of pieces are missing, because these things were built to play chess or, to speak English. They weren't built to, play cyber defense or speak, your network log data. And that keeps us really busy in that kind of interplay between fundamental research and actually applying it in the cyber defense space. Next slide. Okay, so this slide is kind of intended as just a bit of a teaser, what's around the corner. You've kind of got this sense of, that everything to date has been quite simulated, quite abstract. The big picture here is that there really already is quite a large push towards real systems, real attackers, and much more sophisticated agents making use of techniques like self-play or competitive multi-agent reinforcement learning, the kinds of techniques that were used to train very high-performance agents like AlphaZero. We're seeing this already in the offensive space. So at the bottom of the slide, these are two real-world vulnerabilities that were found by deep reinforcement learning agents. And I think we'll only see the scale and scope of that increase drastically over the next few years. The work to date is has been quite narrowly applied to individual APIs or end products. But I do want to impress on you that there is a lot of value there, because these agents are typically trained in a closed box model of the endpoint of the system that we're trying to find vulnerabilities in. And this makes it very accessible to small manufacturers, to startups that want to build a product and have some sense that it might be secure without necessarily, the very expensive experts that can reverse engineer it and find these vulnerabilities in the way it's conventionally done. So I think it's very promising to imagine automated and very sophisticated tools for finding these vulnerabilities before they actually get released into the public. Very kind of lastly, I just hope everyone is excited and aware of the AI cyber challenge by DARPA. It's based on automated detection and patching of vulnerabilities in software, and there's some big prize money available there. So that's surely going to, really increase the amount of academic research that's being done in this space. And also just to touch on products like Purple Llama, which are already bringing automated defensive capabilities to products that include large language models in their design.
I'm conscious we want some time for questions as well, so I'll canter through some cherry-picked examples of policy challenges that we identified through the CETaS research. And probably the main challenge that came up over and over again was about how human-machine teaming in the context of autonomous cyber defense is going to look like in the future. How do we determine what the appropriate levels of autonomy are? What is trustworthy enough to deploy a system like this in an operational environment? What actions should only be permissible in what particular contexts, and what are the authorization limits for the decisions and actions of autonomous agents in autonomous cyber defense? And linked to that, how do we make sure that testing and assurance meets all the requirements of your frontline cyber defenders, but also the people who will have to deal with cyber attacks if, for example, they impact critical national infrastructure? So some examples of requirements that came up through our research include things like observability. So if, let's say, some of the tasks are now being done by autonomous agents, you'd still want your human operator to have oversight over what's happening in the network. But how to do that when the speed is potentially exceeding human capacity? Do you need superhuman speed to address those attacks as well? There are also, of course, requirements around security. You wouldn't want your autonomous agents to be stolen and then reverse engineered by adversaries. Is it directable, as in, if it starts behaving in ways that you don't want, are you able to intervene? Or, do we need a kill switch? Is that a good thing to have? All these questions need to be discussed by all the relevant stakeholders. But aligning on those values and potentially different levels of risk tolerance could take a really long time. And that's the type of timeline that you're looking at as well when you're thinking about deploying a capability like this in an operational environment, besides all the other technical challenges. There are also challenges around developing the skills base, not just to run these systems, but also to build them. I mean, how difficult is it to hire into cyber AI at the moment? How many students are going into STEM, let alone cybersecurity, let alone defense and security, let alone AI cyber for defense and security? These are all things that policymakers need to consider well ahead of the timelines that we're looking at for deployment. We also constantly hear from academics that strategic horizon funding is needed for this work. So to scale up to the ambition, we can't have 2-year grants that basically only allow you to hire in a team and maybe do a few experiments. If you want to do real world experiments and looking at autonomous agents in real systems, then the funding has to match the ambition. But of course, that is always weighed by policymakers amidst lots of competing requirements and lots of competing priorities. So how to galvanize action for autonomous cyber defense is going to be a really important policy challenge. And then there are also issues around from time to time, if these systems make mistakes, or if there are economic losses generated, who's liable? Who's criminally responsible? Is it the CISOs? Is it the people who designed the system? All these questions need to be ironed out before we can deploy a capability. This is just an example of some of the policy challenges that we identified, but like I say, the more comprehensive report is available at cetas.turing.ac.uk if you're interested in seeing the comprehensive findings. So what's next? We need to be seeing what these autonomous agents can do in real systems to bridge the theoretical domain with the operational domain. We need to understand what it's going to be capable of. We need to know the error risks. And that will inform better policy research on what responsible AI looks like for autonomous cyber defense. And we also need more interdisciplinary collaboration, much like the way that AICD and CETaS are working together. At the moment, most of the research is around, on lower left, you can see some levels to the levels of autonomy for autonomous cyber defense, ranging from human-operated systems at level 0 to highly autonomous systems level 4. We're at very, very early stages, so this research needs to be done across all these different levels of autonomy to understand all the possible risks as we scale this up. And we're also starting to look at what sort of actions should be permissible for autonomous agents to do and which should never be permissible. So we're experimenting with looking at the MITRE DEFEND network and what technical experts' views are on what should be acceptable. As you can see, lots of acceptance or stronger acceptance for detect actions, because there are already a lot of industry intrusion detection systems out there that are automated, maybe not using AI, but that are showing promise. But where you look at things like evict actions, a lot of analysts are a lot more conservative about how acceptable they think that would be for if we devolved it to autonomous agents. I hope that gives you a flavor of the way that we work in the Defense and Security Challenge at the Alan Turing Institute and how we reinforce each other's work, but also where we're at the state of the art, some examples of technical and policy challenges. And I think we are ready to take some questions.
Excellent, thank you. We have 3.5 minutes left, so let's see what we can get through. There's some great questions come in on the slider, so I'm going to start with these. One of them is the talk recorded? I would like to watch it again. And as far as I know, the answer is yes. If the answer is no, someone come and tell me before the end and I'll correct it. But there's a couple of quite big general questions which I think are interesting. One, you touched on, how would you counteract bad actors also using these autonomous methods to find vulnerabilities to exploit? Is this just going to turn into an arms race?
I mean, I think it's already an arms race.
Okay, good. Nice short answer. Great. We can get through some more questions. How much of a challenge is the generalizability of these agents to different real-world networks and systems?
I'm hearing lots of different suggestions on this, but Chris can correct me if I'm wrong. But based on the last 2 studies that I've done, it sounds like it's easier and more effective to look at lots of smaller models that are doing really specific tasks on autonomous cyber defense rather than generalizable models. Do you?
I think it's it's probably the biggest challenge we face actually is generalization, particularly with deep reinforcement learning. I think it's striking that you can have an agent that is world class at chess, but it couldn't help you make a cup of tea. Right, it's a very, very specific type of intelligence, and there's no abstract reasoning in the way we would expect a human to think. Transformer models are obviously the most promising in terms of generalization, but there's a lot of work to be done in combining those two domains.
And well, actually leading on slightly from your answer here, there's a couple of related ones. One is that deep reinforcement learning techniques depend on a good model of the environment and a clearly defined reward function. How have you defined a reward function for cyber defense? And a related one, can you share more about what the agents are typically trying to achieve, rewards, and how you represent the state to the agent?
So I think there's maybe 4 questions there. And I can see we've got about 70 seconds. I think we're in quite a privileged situation because we don't need to build all of these simulators. You know, virtualization has been around for decades. We've got really, really good simulators of computer systems and networks. I think let's stop building them. Let's start doing work on real systems. I'm less concerned about the reward. I think ideally the reward would be quite minimal. And again, you know, someone on my team used to work doing reinforcement learning for blood sugar monitoring for diabetes. Now, obviously, it's very difficult in that case to define a reward signal which is keep the patient alive, because you know that's not ethical. But we don't have such hard constraints in cybersecurity. You know, we can emulate millions of these things and cause chaos, but do it in a way that's contained. The very last point on state, though, is very challenging. There's more information than we can actually give to the agents. So developing techniques that identify appropriate state in a broad range of contexts will be really important.
Well, I'm afraid we have now run out of time. Thank you for your questions. And there are several questions that we did not get to, and there's probably people in the room who had questions that I didn't even give you a chance to ask. So thank you very much for that really interesting presentation. And basically, I'm now going to shoo you off the stage and then welcome the next speaker.